Welcome everybody to exercise 3 on page 113 of the workbook. And in this question, we are given the graph of a function little f that's sitting here, and we're given a formula for the definition of a second function capital F that looks like this. Capital F is the integral from -3 to x of little f of t dt. Okay, so in this question, we're going to be talking about two different functions at the same time, little f and capital F. And so it's going to be helpful to know what the relationship between those two functions is. And the key is to think about the second fundamental theorem of calculus here. If you take the derivative of capital F, what you're essentially doing is taking the derivative of an integral. And what does the second fundamental theorem of calculus tell us about that? Well, it tells us that the derivative and the integral essentially cancel in this situation and get us back to the function inside little f of x. So as we're doing this problem, what that tells us is that this function little f over here to the right is the derivative of capital F. Okay, so we are being given the graph of the derivative of capital F, and we're going to be asked a bunch of questions about the function capital F. All right, so keeping that in mind, let's get started with part A here. It asks us for the critical points of capital F, and remember that a critical point is a place where the derivative is equal to 0. Okay? So we've got a graph of the derivative of capital F, so the question is, where is that graph equal to 0? Okay, well, I see 4 points where that happens, and so those 4 points should be the critical points of capital F. All right, so our answers appear to be -5, 0, 3, and 5. And remember how we got those? We just looked at where the graph of the derivative was equal to 0, right on the x-axis. Okay, so we have completed part A. Let's move on to part B here. So this asks us, where is capital F of x increasing and decreasing? Okay, well, we don't have a graph of capital F. What we have is a graph of the derivative. So we need to think about, how do we figure out where a function is increasing or decreasing based on its derivative? Let's start with the increasing part of that. Okay, well, we've been down this road before. A function is increasing where its derivative is positive. Okay, so up above here we have a graph of the derivative. We're simply asking, where is that graph positive? Okay, so I see one interval from here to here where it looks like we're above the x-axis. That's about from -5 to 0, so that should be one of our answers. And then we're above again from 0 to 3. That's another interval where our original function should be increasing. And then finally, from 5 to 6. So we've got 3 intervals where that graph is positive, and those should be the intervals where our original function is increasing. So -5 to 0, 0 to 3, and 5 to 6. Those are the places where capital F is increasing. Okay, and decreasing would just be the exact other way around. Okay, it's going to be decreasing on intervals where the derivative is below the x-axis, and we can go back to our derivative function and notice that there are 2 intervals where we appear to be below. These 2 intervals in green. We just need to write down what those intervals are. So the first one looks to be about -5.8 to -5. Okay, and then another one, let's see, from here to here, that looks to be 3 to 5. Okay, so we have just figured out where capital F is increasing and decreasing. All right, and then we come to C, which is asking us about local maxes and local mins of our function capital F. Okay, so before we dive into that, let's kind of remember graphically what a local maximum looks like. So I'm going to sneak a little picture in for you. So a local maximum of F is a point that kind of looks like this. We come to a peak. And what I'd like you to think about is, how is the derivative behaving on both sides of that local maximum? Well, over here to the left, our function is going up. so the derivative should be positive. And over here on the right, the function's going down, so the derivative should be negative. That gives us a way of identifying where a local maximum should occur. All right, so let's scroll down here a little bit. So capital F has a local maximum at, okay, and the key observation that we made above is that a local maximum occurs where the derivative changes from positive to negative. Okay, so if we scroll back up and look at the graph that we were given, okay, remember this graph is the graph of the derivative. Okay, and I'm going to go ahead and just get rid of some of the markings that we put on the graph earlier. Okay, would be good though to keep the one that says that little f is the derivative of capital F. Do you see a place on that graph where it changes sign from positive to negative? Okay, that would mean we're looking for a point where we go from above the x-axis to below the x-axis. Okay, well I think I only see one point like that, and that would be here at 3. At that point, our derivative graph is going from above to below, so that should mean that the function capital F should have a local maximum there. Right, so x equals 3. Okay, and a local minimum would be exactly the other way around. Okay, so there we're looking for a place where the derivative changes from negative to positive. So if you look back at the graph of our derivative, do you see any places where the derivative graph goes from below to above? Okay, I think I see 2 points like that. So one here at -5 and one here at 5. Both of those places, the graph is going from below the x-axis to above, which means that our function capital F should have minima at both of those 2 points. Let's see, what were those numbers? -5 and 5. Okay, and I believe we've answered part C, and we are ready to move on to part D. And this is maybe the most challenging question so far that we're being asked to answer. So how would we decide where the function capital F is concave up and concave down? Well, concave up is about where the second derivative of our function is positive. But we don't have a graph of the second derivative, we have a graph of the first derivative. So we need to kind of take that statement and turn it into an equivalent statement about the derivative. And if you think about it, the second derivative of a function should be greater than 0 when the first derivative is increasing. Okay, because if the first derivative is increasing, its derivative should be positive. Okay, so to answer the question of where capital F of x is concave up, let's see if we can sneak that statement in here. It's equivalent to asking, on what intervals is the first derivative increasing? Okay, so just to warn you, I'm about to scroll up, and what we're going to do is to try to spot intervals on the derivative graph where that graph is increasing. Okay, so let's see, where is the graph increasing here? So we've got a stretch from here to here where it's going up. There's 1, and then there's another stretch from here to here. That appears to be 0 to 2, and then third and last one from 4 to 6 where we're going up. Okay, so it's those 3 intervals that we want to write down. The first one, let's see, that goes from about -5.8 to, this number's not so nice, but if I had to estimate it, I would say that that's about x equals -2.8 maybe. Okay, so let's scroll back down and just write down those 3 intervals. So -5.8 to -2.8, 0 to 2, and 4 to 6. You can look back up at the graph and confirm that I wrote those down right. Okay, and then similarly, f of x is going to be concave down on intervals where f prime is decreasing. Okay, so where would we be decreasing? Well, let's scroll down again. Okay, and you can see the intervals of decrease are just kind of the opposites of what we had before. So this little stretch here and this little stretch here. Okay, and so if we write down those intervals, we're going to get the second part of our answer. Those appear to be about negative 2.8 to 0 and 2 to 4. Okay, and so we've answered the question about concavity of capital F. Okay, we've got one part to go here, and then we're done. So part E, is asking us to estimate f of 0, capital F of 0. Okay, how would we do that? Well, remember how we defined the function capital F. That was defined to be this integral. So if we want to calculate capital F of 0, we need to plug 0 into that function. So by definition, it would be the integral from negative 3 to 0 of our function. And what does an integral represent again? Well, this represents area. So we have to estimate the area under little f if we want to get a value for capital F of 0. Okay, so if we scroll up and maybe just shade in the area that we're looking for, I'm going to get rid of the stuff that we already marked here. We're really talking about the area from here to there. That's negative 3 to 0. We're asking how would we estimate that area? Okay, well, there are lots of different ways we could do it, but one way would be to use rectangles. Okay, so I'm going to use a little middle sum here, maybe with 3 rectangles, and if we find the middle points and draw in triangles, okay, we could use, or not triangles, rectangles, I'm sorry. If we add up the area of those 3 red rectangles that I just drew in, that would be an estimate of the area that we're looking for. So we need to estimate the heights of these triangles, or there I go again, sorry, rectangles. So the height of this one is, what would you say, maybe about 1.8, and the next one here has a height of maybe about 1.3, and the last one a height of maybe 0.3. Those are just graphical guesses. Okay, and so sorry for all the scrolling, but we're going to go down and just see if we can write down the area of those rectangles one at a time. So the first one had a height of 1.8, its width was 1, and then the next one we estimated its height to be about 1.3 and a width of 1, and the last one a height of about 0.3 and a width of 1. Okay, and you can double check my arithmetic here. We come up with a value of 3.4. That's our best estimate of the area, and therefore our best estimate of capital F of 0.